Okay. Yeah, so let me start by saying, so to thank our speaker. So our speaker is Dr. Pengfei Liang from you're at Inner Mongolia University, right?
Yeah, yeah.
So yeah, let me start by thanking our speaker for agreeing to give a seminar on a recent paper of his, I think in collaboration with Neil Lambert and Maro. If I pronounce your name correctly, I think you're both in the Zoom call as well. So let me just. Yeah. So let me just read out the speaker's bio, and then I'll hand over to Pengfei. So Dr. Pengfei Liang received his PhD degree in Beijing Normal University in 2019. He then moved to Beijing Computational Science Research Center, CSRC, and the Graduate School of China Academy of Engineering Physics for a postdoc. He joined Inner Mongolia University as a researcher in 2024. His current research interests focus on the development of efficient tools for modeling the simulation of open systems and the application in tensor network techniques. So let me say thanks again to our speaker and the people who joined us online. So let me hand over to you, Pengfei.
Okay. Again, let me share my screen. Oh, sorry, there's some problem here. A second. Sorry, I have to rejoin the meeting because I cannot share my screen. Sorry.
Okay, sure. Yeah. That's when you don't have the permissions, right? Oh, is there anything we can do outside, or is it? No. Okay.
I think the system asks you for permission to share this, share that. And
right.
To go to settings, and then we need to go to the meeting and go back to the meeting.
Okay, so I share my screen, right?
Yeah, we can see your screen.
Yeah. Okay, thank you. First I would like to thank you for inviting me here. It's a great chance here for me here to share our recent work. So my name is Pengfei Liang, and now I worked at Inner Mongolia University. So in this talk, I will introduce our recent work about a new simulation method for the modeling and simulation of open quantum systems. Here's the outline of this talk. The first part, because I guess most audience here are experts in this field, so I will just use 3 slides to mention some basic concepts of this in the theory of open quantum systems. So then I will jump to our recent our work. First, I want to apologize because there's some technical details here. Although I try to reduce the amount of technicality here, but I will try to use a minimal example to explain our basic idea and to explain to you what purified pseudomodes are and how to define them. And also, I also with this new method, I will show you that we can model nonlinear system by interaction. So these two works are already on. We already have preprints on arXiv, and we also have another work where we extend this method to fermionic reservoirs. But because we are still preparing the draft, so I will not in this talk I will not mention this one. And lastly, I will make a brief summary. Yeah. So is there any way? Okay. So anyway, so open quantum an open quantum system refers to a system and that couples to its surrounding environment, right? So we can write a very general Hamiltonian for this for an open quantum system. So in this Hamiltonian, you have the HS is Hamiltonian of the system, and HB is Hamiltonian for the bus, and H interaction describes the interaction between the system and the bus.
Sorry, Pengfei, sorry. We can't see your slides changing on your screen. It's just on the title screen. I'm not sure.
Oh. Sorry.
Okay, yeah, we can see it changing now.
Okay. Okay. So can you see it changing now? Because I'm using this full screen mode, but I'm not sure.
At least our side, we can just see the PowerPoint screen, but we can't see you changing between slides.
Now it changed.
Yeah, now we can see you changing. Yeah.
Okay, maybe I can switch to I don't know PDF. Maybe try. Sorry. Second. Yeah, I mean, sorry, because Zoom is a bit difficult. Sorry, how about we do it like this? I mean, I'm not sure because if this is good.
Yeah, let's do it like this now. It's fine.
Yeah, it should be okay for us.
Okay.
Thanks.
Okay. Sorry. Yeah. Anyway, so often we can for many real systems, the bus can be simply seen as a collection of independent modes. So this would distinguish the bus into different classes. Like for instance, if the bus contains a independent harmonic mode or it contains independent fermions, this would correspond to electronic leads, right? And also we also have spin bus, right? So in this talk, I will only I only talk about bosonic bus. And we'll also have another work where we extend this method to fermionic bus. So for a bosonic bus, so the bus Hamiltonian is just a collection. It's a collection of independent harmonic modes. And the most well-studied model in the theory of open quantum systems is called this linear-Gaussian model. So for this model, we write a linear system bus interaction like this. So here S is the coupling operator of the system, and X is some linear operator. So linear here means that it's a linear combination of the cohesion and annihilation operators of the bus. And we also assume that the initial state of the bus is Gaussian, is thermal states. This would mean that the initial state, sorry, the bus free dynamics is, sorry, the initial state is a stationary state under the bus free dynamics. So the bus free correlation functions would be only a function of the time difference. So the one of the fundamental question in the theory of open quantum systems is how can we characterize the environmental effects on the system that the environment couples to, right? So in recent years there are a lot of new methods being developed or still under active developing. But I will not mention those methods. But here I will just talk about the one that which is relevant to this talk. So this is the pseudomode model. So we know that for a linear Gaussian model, we know one important thing is one important fact is that Wick's theorem is valid. So this would mean that any higher order correlation function of the bus can be factorized into a product of the two-time correlation functions. So this would mean that the reduced density matrix of the system would only depend on the two-time correlation functions, which is defined here. And this simple fact means that as long as we have two environments which gives two identical bus environmental correlation functions, then they would give the same reduced density matrix. So this is the basic idea underlining the theory of pseudomodes. So a general pseudomode can be defined by this Lindblad equation here. So in this equation, you can see that we have introduced many dissipative modes. Right? So the dissipation of each mode.
Sorry, Pengfei. I don't think we can see the right slide. We're still on the open. On our side, we just see the open quantum system slide.
Okay.
We can see your pointer moving, but we can't see the slide changing.
So should I? How should I share the screen? Okay, maybe I share the entire screen. Maybe it's good. So how about now?
Okay, yeah, now we can see this. Yeah, now it seems to be working.
I mean, I didn't share the entire screen. Sorry. Yeah. So this Lindblad equation here defines a pseudomode model where we introduce many dissipative modes. Right. So the dissipation is described simply by some Lindblad dissipator here. And the interaction here, we write it as we introduce some coefficient here, and the coupling operator here of each mode is simply is just lambda j times bj plus bj dagger. Right? So this pseudomode, if we decouple the system, then the free correlation function of the provided by this pseudomode would be a sum of exponentials. So this is the correlation ansatz provided by this pseudomode here. So in practice, we can just do some numerical fits of the real correlation function using this ansatz. And once we get a good fit, then we know that this pseudomode will give us at least approximately the reduced density matrix of the original open quantum systems. So this is idea of pseudomodes. Yeah. So in recent years, there are also some several developments of this method. Maybe sorry, I move it up below. Yeah. There are some development of this method. So I will mention two of them. So first, sorry. So first, we can also introduce interactions between pseudomodes. This would give a more complicated correlation ansatz. And this one is developed by the group of Martin Polino in Germany, and also by the group of Johannes Feist, I guess. These two papers are from Johannes Feist. And also one can, because the correlation function is an analytic function of all the model parameters. So one can simply analytically continue all the parameters to the complex plane, to the whole complex plane. So this also gives you a more general correlation ansatz. So this idea, I guess, is from my collaborator Liang Lambert, and also from Grami and Paul Menzel here. These are two extensions of this pseudomode model. So now I just jump to our recent work. We call it purified pseudomode. So I will to introduce this method, I will use a minimum example like this. So here in this model, this minimum model contains only, I mean, the environment is only made of one pseudomode here. So with this minimal example, I will explain what are purified pseudomodes and how to define a purified pseudomodel. So the equation motion of this minimum model is simply written like this. So here I made some simplification that by assuming that the pseudomode is in contact with a zero temperature residual environment. So here that's why here you only see this a dissipator here, a single dissipator here, and the correlation function here. Sorry, do you know if there's any way to hide this because I cannot see the bottom of the slides.
We can see the bottom of the slide. I'm not sure.
Yeah, because on my side, I always see the this. I'm sorry. I mean, I will just move this side part. Yeah, sorry. Anyway, so this mini model, if we compute the bus correlation function for this model is defined at this one. So this XPM is the bus coupling operator, right? So the correlation function is just the correlation function. The correlation function of the bus is just the correlation function of the bus coupling operator. So it's just a single exponential. So now, so we can for this minimum model, we can define a purified pseudomodel by two steps. So the first step, we define a more complex pseudomode model made of two pseudomodes. So this is how we achieve it. So on the right, you'll see what you see is the effective model of this minimum model. So in this model, we introduce two pseudomodes, right? So B plus and B minus. So but here we write their frequency. We make their frequency and complex, and their decay rates. I mean, like this. So this means that we introduce a free parameter A, which is positive and real, for this pseudomode. And the interaction between the pseudomodes and the system, we assume it's the same as the interaction between B modes and S. So this means that the interaction between B plus and S would be lambda S times B plus plus B plus dagger, something like that. And then we can write simply write the equation motion describing this pseudomode model here, and also compute the correlation function for this larger model. And the correlation function for this model has two contributions. So one from the B plus mode and another one from the B minus mode. So the correlation their correlation function just looks at this. So here we have used the fact that the frequency of the pseudomode can be complex. So you see here the frequency of the mode is complex. So to check the equivalence between these two modes, we can do some simple calculation. So here you see that for this minimum model, if we take the positive time part of this minimum, the positive time part of the correlation function of this minimum model, then you can simply write, you can approximate as in this way. Right? So this approximation is just you approximate the step function by exponentials. So in this way, this exponential corresponds is exactly the correlation function of the B plus mode. And on the other hand, we can also write the negative time part of the correlation function. We can also approximate the negative time part in this way. So this would give the correlation function of the B minus mode. Right? And if we sum these two contributions, then you would get some approximation like this. So the original correlation function would be a sum of the C plus and C plus C minus, and with some exponential errors. Here I want to emphasize that this approximation is for non-zero t, because the correlation function always enters into some integral. So if there are some discrepancies at some points, this doesn't matter, right? But later when we talk about nonlinear system bus interactions, the correlation function at t equals 0 will be important. So I will come back to this point on that slide. So this approximation basically tells you that this larger model will give you approximately the reduced density matrix of this minimum model up to some error controlled by this free parameter A. Right? So this is the first step. Then we can, because this error here is exponentially small in A, so we can remove this error simply by sending A to plus infinity, right? So that's the second step. So this step we call it purification. The reason why we call it purification will become clear later. But first, to do this, to see why we can achieve purification, we need to first write the linear equation in the Newell space. So for instance, here I only consider I only put B plus mode here, but the technique developed here can also be applied to the general case. So if we only consider B plus mode, then the linear equation will be this. So then we can do a vectorization to move to the Newell space, right? So this simply means that we change the kits to a block, right? And in the Newell space, then you will get this linear equation becomes something like this. Okay, so in the Newell space, this you have to the original system maps to two copies of the original system. So I use S bar and S tilde to indicate the two copies, and also the B plus mode will be this S bar or B bar correspond to the left action of the B plus or S operators. Right? So S tilde and B tilde will correspond to the right action of the original operators. So in this new representation, we don't have linear dissipator anymore, but we will get some modes with complex frequency, right? So because we have introduced the dissipation and the frequency like in this way, So in the Neuville space, you will see that for the B bar mode, the frequency of the B bar mode does not depend on the free parameter A, but the frequency of the B tiered mode depends on A. So, in fact, this imaginary part of the frequency, you can also consider it as some semi-classical decay, right? So the decay of this B tiered mode becomes gamma plus 2A. This means that the decay of this mode is enhanced, and this is very important for us to achieve this purification. In fact, if we take a limit, if we send A to plus infinity, this would mean that this B-tiered mode is infinitely damped in the limit in this limit, right? And because when we write this pseudomode, we already assume that each pseudomode couples to a zero temperature environment. So this would mean that each mode is initialized in its vacuum state. So these two facts. So first, B-tiered mode is infinitely damped in this limit, and secondly, it's initialized in its vacuum state. These two facts would mean that this B-tiered mode can be, I mean, it basically, during the dynamic evolution, it will just stay in the initial state, right? Because it's damped so hardly, right? So this is intuition underlining this purification technique. Yeah. Yeah. So this slide shows how this adiabatic elimination work. This adiabatic elimination you can do it using the Schrieffer-Wolff transformation. So you use this transformation, you will find that you will get two results. So first, you will get a new interaction between S tilde and B bar, because B bar the frequency we remember that the frequency of the B bar does not depend on A, right? So then when we eliminate the B tilde mode, because in the original linear dissipator there's some interaction term between this B bar and the B tilde mode. So when we do the adiabatic elimination, we will get a new interaction between S tilde and B bar. And secondly, that because this B bar mode is frozen in its initial state, so we can simply drop this mode from the equation motion, right? So in the end, you will arrive at some equation like this by sending A to infinity. So here you'll see that this term is a new interaction mediated by this B tilde mode, and also here we have dropped the terms depending on B tilde because it's irrelevant to the dynamics, right? So if we write this equation back to the density matrix representation, then you will get some equation like this. And this one corresponds to the new interaction. So in this, a very important feature here is that you see that all this B plus operator and they always act on the left side of the density matrix, right? And because sorry, let me jump to the next slide. Yeah. So if we because as I said, this adiabatic elimination technique can be applied to this enlarged two-mode pseudomode model, right? So when you do that, you will get some model like some equation motion like this. So in this equation motion, in the first line, you see that in this red box, this B plus operator only acts on the left-hand side of the density matrix, and this B minus mode only acts on the right-hand side. So, and also because we we remember that the initial states of this mode are always vacuum states, right? So this would mean that the reduced density matrix of the B plus mode will look like this. So only the broad parts of will change, right, during the dynamics. And the B minus mode, because it only acts on the right, so the reduced density matrix for this mode will looks like this. Yeah. So only the cat part of the density matrix change during the dynamics. So this is the reason why we call it purified pseudomode, because for this kind of states, you really don't need the density matrix. You only need a pure state to describe the state of this mode. And in this plot, I just so I show this by this gray shading here to indicate that the B plus mode only act on the left, and the B minus mode only act on the right. So this is what we call the purified pseudomode model. So yeah, so here this is a short summary of a brief summary of the whole procedure. So it contains two steps. So first, you build a larger pseudomode model, which by introducing this free parameter. And with this, because of this free parameter here, you will have some error, some extra error in this model, right? But then you can remove this error by doing this purification. Then in the end, you will arrive at this purified pseudomode model, which is exactly equivalent to the original model. Yeah. So this two steps is a general procedure to define a purified pseudomode model. Yeah, so here I summarize, I compare the difference, compare the concept of pseudomodes and purified pseudomodes. So as you can see, the state of a pseudomode is always mixed, right? And the state of the purified pseudomode is essentially pure, right? It's a pure state. And if you look at the correlation function, the free correlation function of the pseudomode, it looks like something like this. So it's exponentially, it decays exponentially on both sides of the, on both the negative time and positive time. Right? Here I didn't plot the most general correlation function of the pseudomode, because I mentioned that the correlation function of the pseudomode the frequency and the decay rate can be complex. So in principle, the correlation function of the pseudomode can be more general than this. But the main point here is that the correlation function of the pseudomode will not vanish on either the positive time or negative time. Right? And for purified pseudomode, you can see that either the negative time or the positive time correlation becomes zero. So this is the correlation function for the purified pseudomode. And the initial states, because the initial state of the purified pseudomode is always a vacuum state, because we start from the zero temperature, the pseudomode in contact with zero temperature environment. Right? So, but in general, the initial state of a pseudomode can be more general, can be any thermal state. Yeah. So another point I want to mention is that, in fact, after we developed this approach, we gradually realized that this left and right acting of this purified pseudomode, actually one can rewrite the equation motion as a hierarchy equation motion. So this method is very popular in the physical chemistry community. So in fact, this equation motion is we can show that this purified pseudomode, if we only consider the system dynamics, is completely equivalent to to the Hume developed in this paper. And also this kind of equivalence between pseudomode model and HOM is all, I mean, it's all also realized in this paper. Yeah. Yeah. So far I only introduced this the idea of this of our work of this purified pseudomodes with a minimum model. So how does this work for a general linear-Gaussian model? So you can define, in fact, you can define a purified pseudomode with 3 steps. So first, we take the positive or negative parts of the correlation function and use some existing decomposition algorithm to write it as a sum of exponentials. Because this is one main advantage of this purified pseudomode because of this existing decomposition algorithms. You can do it very easily. And in the second step, you simply, for each exponential in this sum, you write it, you approximate as an exponential in this way. Here I only write the positive time part, but the negative time part you can easily get it using the time reversal property. And then lastly, you just do the purification by sending A to infinity. Then you will get a general the desired purified pseudomode model. So why should we use purified pseudomode or why instead of pure pseudomode? So first you can see that by writing from this minimum model, you can see that by writing this by split one pseudomode into 2 purified pseudomodes, we don't get any memory optimization, right? Because the original one pseudomode, if we use the same truncation, then the Hilbert space, the memory cost for the 2 models are the same. So in general, actually, if you have an n pseudomode model, you can always write it as an equivalent to n purified pseudomode, but not vice versa. This is not good for if you are using solvers like some master equation solvers to solve the equation motion of these 2 models. But one, as I mentioned, one advantage of this purified pseudomode model is that it makes the definition of the model much easier than much easier. Because for conventional pseudomode model, if you want to fit the correlation function for both the positive time and the negative time part, there are no existing algorithms like this. These algorithms can do that, right? But for the purified pseudomode, you can do it very easily with these algorithms. And another advantage of this purified pseudomode is that when you consider to simulate the equation motion by using tensor networks, because when you use the tensor networks to do the simulation, you will find that this reduction of the local this purification of the pseudomode state will give you a huge reduction of the computational complexity of the tensor network algorithm. So these 2 are the main advantage of the purified pseudomode compared to the conventional pseudomodes. Yeah, so here I show you a simple test for this method. This is really not a test because as I mentioned, we can actually prove exactly that this when only consider the system dynamics, our purified pseudomode method is equivalent to this hierarchical motion. So here I'm comparing with this this equivalent hierarchical motion. So for sure you will see that the simulation results coincide. But this numerical results at least show you that this equivalence is indeed true, right? So here I show the spin the polarization dynamics of the spin boson model for a sub-ohmic spectral density. Yeah, so now I will mention two extensions of this purified pseudomode. So first, I will show you how to model bus input output with this method. So first, we know that for conventional, especially for many methods like here I list a few like pseudomodes or HOM and also tempo. These methods they are based on they rely on the Feynman-Verloc influence function. Right? So as far as I know, methods rely on Feynman-Verloc influence functional do not allow you to track directly the evolution of any bus observables. Although we know that there are some indirect way to compute the bus observables, like you can relate your bus observable to some system correlation functions. But that's an indirect way, right? And also, it doesn't allow you to model any non-Gaussian bus initial states. But here I'll also use this minimal example to show you that how we can achieve this how we can model bus input output. But here I will only show you how to compute bus observables. But for inputs, it's a bit more complicated, so I don't do it here. So anyways, so our main goal is to calculate the expansion value of this of the B operator. And this is not in the scope of the conventional pseudomode model, right? And the conventional pseudomode model that doesn't allow you to compute quantities like this. So our solution is just to use Wick's theorem. So if you use Wick's theorem to factorize this, to decompose this this quantity, then you will see that the expansion of B will depend. I mean, not only depends on the correlation function C of t, right? It also depends on an extra bus correlation function like this. So it's a cross correlation between the bus observable and your bus coupling operator. So to see this, we can do a simple calculation. So if in the Dyson series of in the Dyson expansion of this quantity, then the first order of in the Dyson series will depend on this correlation function. So this is exactly the extra correlation function here, right? And the third order, if you write it down explicitly, it's like this. And for this correlation function, you can use Wick's theorem to factorize it. So you will have terms like this, right? So this terms is just it's a multiplication of this extra bus correlation function and your original the original correlation function. Right? So this simple exercise means that tells us that if we want to compute this quantity, then we should find a way to model this extra cross correlation function. So then I will show you how to do it with purified pseudomodes. So it's actually also quite simple. Actually, for this minimum model, so first we also need this B plus and B minus mode here. because they are responsible for the system that to give you the correct system dynamics. But here we can also introduce an extra mode, which is BO. This mode, because in the previous slides you can in the previous slides you can see that you can see here this actual bus correlation function, we actually only need the positive time part of this actual bus correlation function. Right? We don't need the whole cross correlation function, because here t is always larger than the tau here, because tau is it's in the integral. Right? Yeah. So this means that we can define. So for this actual pseudomode here, we can define we need because we will need to model this positive time correlation function. So it's for that purpose, the frequency of this actual mode should we should write it like this. Right? It's plus IA. And the decay rate also, for sure, it's gamma plus A. Another point here is that we need to carefully design the interaction between this mode and the system. Because once we introduce, if we don't do it carefully, then we may change the system dynamics. Right? So here we define the coupling between the system and this mode as S times S XO. So this XO is only depends on B dagger. So this kind of modes, if you do a simple calculation, then you will find that the correlation function between X, the coupling operator, is 0. So this means that this kind of modes, we call it dangling modes, they will not contribute to they have a 0 self correlation function. So this means that they don't change the reduced system dynamics. Right? But with this mode, if you compute the correlation function, the cross correlation function defined like this, then you will see that it's exactly the actual correlation function we want to model. Yeah. So this equality tells you that this three-mode pseudomode model will, by computing the exponential value of this BO operator, then you will get approximately the exponential value of the original B operator. Right? So after you define this, then you can just do the purification by sending A to infinity, and in this way you will arrive at some purified pseudomode model, which where you remove this actual error. And so with this purified pseudomode model, then you will have some an inequality here, right? So the exponential value, if you compute the exponential value of the BO operator using this model, then you will get exactly the value of the exponential value of the B operator in the original in the minimum model. So this is how we model this bus output, and for input, one can just set this t to 0. Then you can do it in a similar way. So and with both input and output, it's a bit more complicated, because in that case you need to you need to also consider some cross correlation between the field this observables. But in principle, you can always define a purified pseudomode model to model any bus input output. Yeah, so here I will show you a more practical example. So in this case, we consider the okay. So here we consider a model. It's called so here there are two quantum emitters, E1 and E2. So each one couples to a local cavity, C1 and C2. So the distance between these two cavities can be very large because this is a schematic plot of some of a photonic crystal because this kind of system can be realized in it's already realized in a recent experiment. So in this model, we checked for instance in the first plot, what you see here is the population dynamics of these two emitters. But here we make this the distance of these two between these two cavities small. I mean the distance is small compared to the wavelengths of the emitted by the two emitters. Yeah. So and because all the emitters and the cavities are in resonance. So here you'll see some Rabi oscillation. Yeah, for this light blue and light yellow color, right? So you see this. Sorry, you see this Rabi oscillation, and then we increase the distance between the two cavities so in this plot, if my memory is correct, then for this dark blue and dark orange solid lines, the distance between the two cavities is around 14,000 times the wavelength of the light. So here, then you will see you can have a visible time retardation effects. So because the only the emitter one is initially only emitter one is excited. So only after a finite time, the second emitter will see the light emitted by the emitter one. So for this very large separation, the dynamics of these two emitters will be very non-Markovian. So that's why we chose this model to test our methods. And then we also test to initialize both emitters. And then you will see, and for this very large separation, then you will see some complex behavior, dynamic behavior, and we also test a non-Gaussian initial state for the two cavities. So here the initial state is a single photon state in cavity one. So this one would tell you that we can our method can give you can model bus input and output. Right? Yeah. So the last the next extension is to model nonlinear system bus interactions. So yeah, sorry, I cannot see. Yeah. So to my knowledge, to the best of my knowledge, so most non-perturbative methods only consider linear system bus interactions. So we only know two papers that considered nonlinear system bus interactions. So with this, again, with this minimal example, I will show you that in fact the purified model can model any very general nonlinear system bus interactions. So here in this case, we assume that the system bus interaction is no longer this linear in this linear form. In turn, we assume a general system bus interaction like this. So S times Q. Q is some analytic function of this of the linear coupling operator. So this means that this Q operator can be expanded as a series of this X operator. Right? So our question is, how can we evaluate the reduced density matrix in this case? So our answer is again Wick's theorem. So if you apply Wick's theorem to this, in this case, you will find that the reduced density matrix not only depends on the in the Dyson series, you will not apart from the two-time correlation function, you will also get explicitly the second moment of the linear coupling operator here. So we can also do a simple exercise to confirm this. So for example, if this Q operator is x squared, then in the first order of the Dyson series, you have this term. So it depends on the second moment of the linear operator, and in the second order you have Q of T2 and times Q of T1, and this one you can also use Wick's theorem to factorize, and then you get the second line. So in the second line you also get the second moment of the linear coupling operator. Yeah. So this is a main difference compared to the linear case. In the linear case, you don't have this x squared term in the Dyson series. So to model this kind of general nonlinear system-bus interactions, we can also proceed along similar lines. So first we try to define a pseudomode model that's in a similar way that give you the approximately the reduced density matrix of the original of this minimum model. Then we do the purification. Right? So to define this model, we still need this B plus and B minus mode because they will give you the correlation function at non-zero time. Yeah. But in this case, we also need an extra mode, which has zero frequency. So the correlation function of this mode looks like this. So you see that it's just the frequency is zero. But this one, if we add this zero frequency mode here, then you will find that the original correlation function, you can approximate the original correlation function as the sum of the C plus and C minus, and also this C zero frequency, right? And the error for this approximation is again exponentially small, but in this case it's exponentially small for all t, for all real t. If you remember in the linear case, we mentioned that we only need this two term, but with this two term, then this approximation, this error, this exponential error is only true for non-zero t. Right? Because in this nonlinear case, the second moment appear explicitly in the Dyson series. So we also need to recover this the correlation function at zero time. This is the main difference. Then we do the purification. Then we arrive at a purified pseudomode model, which will give you the same reduced density matrix as this minimum model. And here you don't see any purified pseudomode correspond to this zero frequency pseudomode, because when we do a purification, because its frequency is zero, when you do the purification, this mode just simply vanish, and this mode will give you some effective Hamiltonian, which is absorbed in this other two modes. Okay. Yeah. Then this is a simple test for this approach. So here we consider the system is just a single a two-level system, and the coupling operator is sigma s, and the bus coupling operator, we assume it has three contributions, x and x squared, and also s cubic. Yeah. So in this, so here we test this value, these three values correspond to alpha 1, alpha 2, and alpha 3. So this is a linear case. We only have alpha 1, where Q equals xpm. And in this case, we have a quadratic correction, and for the green line, we have a cubic correction. Yeah, and these two lines have a cubic correction. So we compare this the results of this this purified solid model to the original minimum model. So you see that the coincidence for in all cases. Yeah. So now I will just summarize this talk. So in this talk, I introduced to you a new method, which is based on purified pseudomodes, and this method is aimed to model general nonlinear Gaussian bus, and the concept of purified the concept of purified pseudomode we introduced here can be easily combined with pseudomodes to define some hybrid method. And third, I showed you how we can use this method to model bus input output and also nonlinear system bus interactions. Yeah. Finally, I want to thank my collaborators, Mauro and also Neil. Thank you. With this, I will thank you for your attention.
Cool. Thank you so much for that really interesting talk. I have a couple of questions. I don't know, maybe I can ask them first.
No, can I ask one question first? Because I need to answer somewhere else. Sorry, thank you very much. It was really very nice. Just one stupid question. Is there any of your purified models, yeah, or versions that allows for some interesting unraveling?
Sorry, can you repeat again? Because here, I mean...
Sorry, you take the simplest purified pseudomode approach that you have, yeah? Yeah. Does that lead to some interesting unraveling that is maybe a little bit different from the traditional ones?
I'm not sure if I understand the question, but
you know, once you have, usually when you have a linear master equation and you do a kind of a purified version, you can unravel it into a kind of a stochastic Schrödinger equation. Yeah? Yeah. Does your pseudomode, your purified pseudomode approach lead to some interesting stochastic Schrödinger equation for the wave function?
Sorry, I mean...
maybe it's a topic for another time. Yeah.
Sorry, I mean, because for the first stochastic stuff, I'm really not, I don't understand too much about that.
Okay, no worries. Maybe we can discuss it another time. Yeah.
Okay, sorry.
Sorry, I need to leave now.
Okay.
I made you co-host.
Okay. I had a question about, I think you had the slide where you compared the purified method with the standard pseudomode method. Yeah. A couple slides down from the current one.
Yeah.
You keep going.
Yeah.
Yeah, it's the one below this one. Okay. The next slide. Yeah, this one. Okay. So my understanding is that in your approach, so you you effectively start with one pseudomode, you map it to two pseudomodes, where each of these pseudomodes that have this complex frequencies, they only one of them accounts for the time dependence of the correlation function on the positive time axis, and the other one accounts for the time dependence in the negative time axis.
Yes.
And I assume that the frequencies of these pseudomodes, so one of them is like nu plus IA, the other one is nu minus IA, right?
Yeah, yeah.
And so you need the symmetry to account for like the correct symmetry in the correlation function. On this slide as well, you mentioned that lambda is complex. Would that also mean that, I mean, is that possible in general, or would that also mean that you have to have non-Hermitian system pseudomode couplings as well, in addition to the fact that you have these additional complex frequencies?
Okay, that's a good point. So, in fact, so if the value, if this lambda j here is real, right? So you really don't need any purified zone, because you can very easily define a certain model, right? Because we already give you a certain model, right? So, but in general, when you fit or when you get this decomposition with this using these algorithms, in general you will find that the coefficient here is complex. So there's no easy way to make sure that you always get a real coefficient here. And I mean, this is one reason that why we move in this direction, because if we impose this constraints that these coefficients are real, the fitting of the correlation function will become sometimes, I mean, because if, for instance, if you use least square, then you will find that in many cases the fitting will just get stuck in some local minimum solution. Composition. You don't get a equilibrium. Yeah.
I was more interested in the fact that, so I understand that lambda is complex, but in the second line you write that you have the lambda squared as like the pseudomode. So the lambda squared there is going to be complex as well, right? Which would imply that map that to your pseudomode model, then the system pseudomode couplings are also going to be non-Hermitian.
Yeah, yeah.
Do you also incorporate that into like the model as well, this non-Hermitian aspect? Because I know there's also other work that's been done with like the pseudomode method where you have complex systems.
I'm not sure if you can call this model non-Hermitian, because one important thing is that we don't do the complex conjugate the complex conjugate in the linear equation in the master equation, right? So, for instance, even if this lambda is complex, when you define in the model, maybe I go back a bit. Maybe I go back to the. Yeah. For instance, here, if this lambda is complex, so we then I mean, as far as I know, that in the Hermitian physics, the commutative is defined like as h rho minus rho h dagger, right? But here we don't do that. So it's all even if this lambda is even if this lambda is complex, you always write it as h rho minus rho h. You don't do the complex conjugation, because this complex conjugation we are just I mean, because we argue that we can make the coefficient and all these parameters complex because we're using analytical continuation. If you have complex conjugates, then you cannot you don't have analytical continuation, right?
Okay, yeah. And my second question was more just trying to understand. So with these purified pseudomodes, the kind of the advantage is that you massively reduce the memory cost because your pseudomodes basically don't get occupied. You said that you can adiabatically eliminate. There's some kind of adiabatic elimination, right?
Yeah.
So the advantage is that you can reduce the memory requirements because of this adiabatic elimination, but you have to double the number of pseudomodes.
There's no memory optimization here, because for instance, if you go back to this model right here, when we, for instance here, because we double the number of modes, so how to say it? I mean the space of this the size of this total of this for this two pseudomodes for this two modes is the same as the original mode, original B mode. So in fact, the memory cost for two mode for pseudomodes and corresponding purified pseudomodes are the same. But the advantage is because here I don't do the detailed analysis here. But if you use tensor network, when you use tensor network, when you compute the computational complexity, then you will see that this reduction of the I mean this change from a mixed state to pure state will give you a reduction of the computational complexity of this network algorithm. That's a main advantage. I mean, that's why I said if you don't use solvers like tensor networks, then basically this purified student model doesn't give you too much advantage.
Okay. Also, just one final question from me. Is this purification approach somehow connected to like thermofield mapping? Do you know? Are you aware of like the thermofield mapping?
I see. Yeah, that's also in that case, people also call it purification, right? But in this case, we actually get this purification by doing some adiabatic elimination, right? In that case, I guess it's not like this. I think there are different things, I think.
Okay. Okay, great. Is there any questions from anybody in the chat? Like, please feel free to just unmute yourself. You should be able to unmute yourself if you have a question. Okay, if there's no questions, then let me just say thanks again to the speaker. And yeah, hope you all have a good afternoon or evening wherever you are in the world. So cool. Thanks again.
Thank you.
Thank you.